Hello and welcome to ControllersTech. This is the 7th video in the STM32 USB series. We will continue using the STM32 as a USB device. We have already covered how to emulate the STM32 as a mouse and keyboard, but separately. Today, we will combine both the mouse and keyboard into a single project, so the STM32 will act as both a mouse and a keyboard at the same time. Unlike the previous video, we will not use the Composite USB class. Instead, we will use only one HID class, and using that, we will send data for both the mouse and the keyboard. Before continuing with this video, make sure you have watched the mouse and keyboard video and that both are working fine separately. I will not explain everything in detail here, and mainly focus on how to integrate both devices into one. I have also downloaded the mouse and keyboard project from the previous video, as we would need to copy the working code from it. Let us start by looking at the connections we are going to use in this project. I have used an analog joystick for mouse control. The joystick is connected to the ADC of the STM32. The X-axis pin is connected to pin PA1, which is ADC 1 channel 1. The Y-axis pin is connected to PA3, which is ADC 1 channel 3. The switch pin of the joystick to PA5, and we will configure that as an input. This switch button will be used as the middle button for the mouse. I have also added two more buttons, one for left click and one for right click. The buttons are connected to pins PA7 and PC5 respectively. The other end of each button is connected to ground, so when you press a button, the respective pin gets pulled low, which tells us that the button has been pressed. The joystick is powered from the 3.3 volt supply of the development board itself. Now let's look at the keyboard connections. I am going to use a 4x4 membrane keypad here. This keypad has 8 pins, 4 row pins and 4 column pins. These are connected to the STM32 starting from pin PB2, all the way up to PC2. The row pins will be configured as outputs, and we pull one of them low at a time. The column pins will be configured as inputs, so when you press a key, the respective column pin gets connected to the active row pin, and is pulled low. That is how we identify which key was pressed. The data from both the joystick and the keypad will be transmitted over USB, and the computer will recognize it as input from a mouse and a keyboard. Now that we understand how the connections work, let us open STM32 CubeMX and create a new project. I am using the STM32 F446 development board from React Studio for this project. This board has an 8 MHz crystal on it, so we will enable the high-speed external crystal to provide the clock. Since the board has an 8 MHz crystal, we will use the PLL to run the system at the maximum possible clock speed of 180 MHz. Next, go to sys and enable serial wire debug. Now let's start with the ADC configuration. Enable channel 1 and channel 3 of ADC 1, and you can see that pins PA1 and PA3 are enabled automatically. These are the pins where the X and Y axis outputs of the joystick are connected. Next, set the ADC resolution to 8 bits, as the mouse descriptor requires 8-bit data. If you are using the STM32 F103, you cannot change the resolution, the default is 12 bits. So you will need to map the 12-bit data to 8 bits before sending it via the HID class. That has already been covered in the mouse video, so take a look there if you are using the F103. Since we are using 2 channels, we need to enable DMA for data transfer. Make sure DMA is enabled in circular mode, and the data width should match the resolution. In this case, it is set to byte. Now go back to parameter settings and change the number of conversions to 2, since we have 2 channels to convert. Scan conversion mode will be enabled automatically. Make sure to also enable continuous conversion mode and DMA request. Also make sure the end of conversion selection is set to end of all conversions, so the DMA interrupt only triggers when both conversions are complete. Now let us configure the ranks. Rank 1 is set to channel 1, set the sampling time to the maximum, as we do not want the interrupt triggering at a very high rate. Set rank 2 to channel 3 and also set the sampling time to the maximum, which is 480 cycles. That completes the ADC configuration. Now set the pins PA5, PA7, and PC5 as input pins. These are the pins where the buttons are connected. Also provide a user label for each pin according to its button function, just like we did in the mouse video. Then go to System Core, open the GPIO tab, and make sure all 3 pins are configured with pull-up. This way, the pins will be high by default, and when a button is pressed, the respective pin will be pulled low, indicating that the button has been pressed. Now let us configure the pins for the keyboard. Starting with the row pins, configure PB2, PB0, PC4, and PA6 as output pins. These are the pins where the rows are connected. So provide user labels for them from R1 to R4. Next, configure PA4, PA2, PA0, and PC2 as input pins. These are the column pins from the keypad. Name them accordingly from C1 to C4. In the GPIO section, select all the column pins and enable pull-up for them. By default, all column pins will be pulled high, and when any key is pressed, the respective column pin will get connected to the row pin that is being pulled low. Also make sure all the row pins are high by default. We will pull them low one at a time inside our code. That completes the mouse and keyboard pin configuration. Now we will configure the USB. Go to USB OTGFS, and enable it in device-only mode. No other configuration changes are needed here. Then go to Middleware, open USB device, and set the class to Human Interface Device. Leave everything else at default. As explained in the previous video, note that the polling interval is set to 0xA, which means 10 milliseconds. This means the host will poll the device every 10 milliseconds, and our program should be written accordingly. Sending data more frequently than that will have no effect, as the host will only read it once per polling interval. Now go to the clock configuration. You will notice an error there. That is because the USB peripheral is currently receiving the 180 MHz clock. We need to adjust the PLL multipliers and dividers, so that the USB peripheral receives exactly 48 MHz. Finally, go to the Project Manager, provide a name for the project. Make sure the toolchain is set to STM32 Cube IDE, and click Generate to generate the project. The project has been generated, so now we will import it into STM32 Cube IDE. The project has been imported, and here is our main file. Before we proceed with implementing both the keyboard and mouse, we need to test the mouse alone first. Go to Middleware, then STM32 USB Device Library, then HID Class, and open the file named usbhid.c. Here you can see that by default, CubeMX generates the descriptors for a mouse. Since the descriptors are already included in the generated project, we only need to write the main file. I am going to copy the relevant functions from the mouse project, downloaded earlier, and paste them at the appropriate locations inside the main file. The pin names are the same as what we defined in the mouse project, so there should be no compatibility issues. Let us build the project. We have one error, that is because the HID header file has not been included. Let me include the USB HID.h header file and build the project again. Now there are no errors. Let's take a quick look at this project. Once the ADC finishes converting both channels, it calls the conversion complete callback. Inside that callback, we store the data in the HID buffer. Since mouse movement data is relative, depending on which side the joystick is tilted, we send a value of 5, indicating that the mouse should move 5 pixels to the left or right. The same applies to the y-axis, it moves 5 pixels up or down. Inside the infinite loop, we check which button is pressed, and depending on that, the corresponding data is loaded into the 0th element of the HID buffer. Finally, the data is sent using the HID send report function, where we send 4 bytes of mouse data. The project has been flashed to the board. Let me test it by moving the joystick. As you can see, the movements are smooth, the joystick is responding well, and the buttons are also working correctly. So the mouse project alone is working just fine. Now we need to add the keyboard data into this project as well. As mentioned earlier, we are not going to use a composite USB class, instead, we will modify how the data is transmitted. The first thing we need to do is add the keyboard descriptors to our project. Open the keyboard project from the previous video, browse to middleware, then the USB device library, then HID class, and open the USB HID source file. We have already defined the keyboard descriptors in the previous keyboard video, so we are going to simply copy them and paste them into the HID source file of our current project. Make sure to paste them below the existing mouse descriptors. You will notice an error after pasting, that is because the mouse descriptor array was closed before our addition. We need to add a comma after the last entry of the mouse descriptors, indicating that there are more entries below. The error should now be gone, and we have both the mouse and keyboard descriptors together inside the descriptor array. Now, inside the mouse descriptors, after the collection opens, that is, after the 0xa1 command, we need to add a report ID for the mouse. We will set it to 1, indicating that this is the mouse descriptor. Similarly, we need to add a report ID inside the keyboard descriptors as well, but it must be different. We will set it to 2. So the report ID 1 is for the mouse, and report ID 2 is for the keyboard. Next, we need to update the descriptor size in the USB HID header file. Right now, the size is set to 74, which accounts for the mouse descriptors only. We have now added the keyboard descriptors as well as the report ID fields. The keyboard descriptor is 43 bytes, you can verify this in the keyboard project. We also have 4 additional bytes in total for the 2 report ID fields. So the updated size is 74 bytes for the mouse, plus 43 bytes for the keyboard, plus 4 bytes for the report IDs. Next is the endpoint size, which is currently set to 4. That is correct for the mouse alone, it uses 1 byte for the button, 1 byte for the x-axis, 1 byte for the y-axis, and 1 byte for the wheel, giving a total of 4 bytes. However, with the report ID included, the mouse will now use 5 bytes in total. The keyboard uses 8 bytes, 1 byte for the modifier, 1 reserved byte, and 6 bytes for the key codes. With the report ID byte added, the keyboard will use 9 bytes in total. Since the endpoint size must accommodate the largest packet, and the keyboard requires 9 bytes while the mouse requires 5, we will set the endpoint size to 9. Now let us go back to the main file and modify the mouse buffer. Earlier, the mouse buffer used 4 bytes, but now since we are including the report ID field, it will need 1 additional byte, making it 5 bytes in total. The report ID will occupy the 0th element of the buffer, which means all the other data will shift 1 place to the right. So the x-axis data, which was previously stored in the first element, will now move to the second element. The y-axis data, which was in the second element, will now move to the third element. The button data, which was stored in the 0th element, will now move to the first element. We will store report ID 1 in the 0th element to identify this as mouse data. Since we are also going to create a separate buffer for the keyboard, it is a good idea to rename the buffers according to their functions. So let's rename the existing HID buffer to mouse buffer, so it is clear that this buffer holds the mouse data. The renaming is done, and our mouse data is now ready to be sent. Now we will add the keyboard data as well. I am going to copy the relevant functions from the keyboard project, and paste them at the appropriate locations inside the main file. Alright, now start by modifying the keyboard buffer. I am renaming the HID buffer to keyboard buffer, so it is clear that this buffer holds the keyboard data. In the previous keyboard project, the buffer used 8 bytes, but since we are now including the report ID field as well, it will need 9 bytes in total. The scan keypad function stores the data in the key code and modifier variables, so we do not need to modify anything there. Now, inside the infinite loop, after scanning the keypad, we need to store the report ID in the 0th element of the keyboard buffer. We will store report ID 2 here to identify this as keyboard data. The modifier, which was previously stored in the 0th element, will now move to the 1st element, and the key code will be stored in the 3rd element. So in total, the keyboard buffer uses 9 bytes. The sendReport function will now send 9 bytes for the keyboard data, and 5 bytes for the mouse data. Let us build the project. There seems to be an issue in the used HID source file. I have used the wrong size for the report ID field. It should have been 4 bytes in total for both report IDs. That has been corrected, and the project now builds successfully. Let us flash it to the board. Now let's test the keyboard and mouse response. I am going to start with the mouse first. The mouse is working fine, but the movement has slowed down drastically compared to before. The keyboard is responding well. So both are working, but the mouse is too slow. Let us fix that. The mouse data is currently being sent every 20 milliseconds. I am going to reduce both delay values to 5 milliseconds. Also increase the movement to 10 pixels at a time, so the mouse movement will be noticeably faster. Let us flash the project again. The mouse movement is much better now, it is moving fast compared to before. The keyboard is also responding well, and it is still programmed the same way as in the previous project. The 0 key is mapped to space, the hash key is mapped to delete, and the star key is mapped to shift. Both the mouse and keyboard are now working correctly over a single USB connection. The STM32 is successfully emulating both a mouse and a keyboard simultaneously, using just one HID class and one USB interface. That is it for this video. I hope the explanation was clear, and you now understand how to implement both a mouse and a keyboard over a single USB connection, without using the Composite USB class. You can download the project from the article linked in the description. Leave a comment if you have any questions or suggestions. Keep watching, and have a nice day.